All right. Hello, everyone. Welcome to this technical session brought to you by Amoye. Amoye is an edtech startup with a mission to prepare young professionals and college students for their career choices in data and future of work. We do that via our internship programs, which simulate the conditions you will face while working in a real-world environment, real work environment. Our internships will expose you to specially designed courses and career coaching webinars with industry experts and industry relevant project presentations like what we are having right now. My name is Mercy, and my job at Amoye is to make sure you have a smooth experience. I'm joining you from Ibadan, Nigeria, and I'll be your host for today's session. I'd like to welcome to this event everyone present, our incredible interns in the current cohort. Kudos to you for making it this far. Thanks to the Amoye Fellows and the Amoye team who have made this session possible. For this session, we have an industry expert, Mr. Oladimeji Mudele. Oladimeji Mudele is a postdoctoral fellow at Harvard TH Chan School of Public Health. He obtained a B Engineering honors in Bachelor's of Engineering in Electrical and Electronics Engineering from the Federal University of Technology, Akure, Nigeria, and also holds an MSc in Electronic Engineering, summa cum laude. Oladimeji has a PhD in Electronic, Computer Science, and Electrical Engineering in the year 2021 from the University of Pavia, Italy. His work centers on the application of geospatial information and data science methods for connecting climate and health outcomes policy. He was a beneficiary of the Marie Sklodowska-Curie Actions and the German Academic Exchange Service scholarships. Between 2018 and 2019, he was a visiting scholar at the Argentinian Commission for Space Activities and the Institute of Computing of the Federal University of Alagoas, Brazil. In 2019, he received the Premio de Laurea Award as the top international scholar in UNIPIV. Okay, I don't know how to pronounce that. As an employee at VoiceAid, he co-built a text-to-speech technology engine using deep learning-based methods, including convolutional neural networks, transformers, recurrent neural networks, self-supervised learning, adversarial learning, among others. He will be sharing his thoughts and experience on the topic, correcting readings from low-cost air quality sensors using statistical methods. But before I hand over to Mr. Oladimeji, please carefully take note of the following. Feel free to post your questions and comments on slido.com using the event code 3708257. Once again, the event code is 3708257 on Slido. And, they'll be promptly attended to. As you know, Mr. Oladimeji will be taking us through two sessions. First, the technical session, and then the question and answer session. A Google form will be opened, will be updated, a Google form link will be posted right now to collect attendance for the Spring 23 cohorts interns present in this technical session. Use the secret code FLASK, all lowercase, FLASK, FLASK. FLASK, all lowercase, and I'm sure the form link are being posted right now on Zoom and on YouTube alone. The form will be open for 10 minutes starting now. We have pinned the attendance form link on YouTube and Zoom. We want you to fill your form quickly in order to focus on the presentation. You're welcome, Mr. Oladimeji. It's over to you from here. Thank you very much for coming.
All right. Hi everyone. Good morning or good afternoon. Sorry, because it's morning over here. It's 9 o'clock. I see some people are still coming in. Do we want to jump in and then already, whoever joins us in the middle, then might. We will try to minimize the amount of content that people will miss within the first 5 minutes of the call of the talk, and then from that point, whoever comes in late might miss quite a lot. All right, so everyone, I want to share my screen now. I'm trying to get the presentation up, and then I'll just share it. I'm coming in just a moment.
Right.
Let me share my screen. It's going to be this one here. So you can see this one, right?
Yes, we can
Okay.
see. We can see
So you can
the.
see my screen, right? You can
Yes, we
see my
can.
screen already. Okay. So welcome to this presentation. Interestingly, I had already given something around the same topic to this same organization, but I mean, I think that should be a different cohort. And I understand that some of you have already been exposed to those materials that had been shared the last time, because the last time I shared uh, um, a bunch of code that you could use to experiment around the subject that I'm going to be talking about. So we're just going to be doing the same thing today. We just go through you. Maybe some of you have already seen the slides because if it had been shared before. So we will just go through them. I mean, talk very lightly about them, try to be as high level as possible so I don't get into too much of the details. And then after that, we will go into, just checking through the GitHub repository that some of you also have access to. So yeah, let me quickly run through the start of this talk. Um, if some of you have been in the news recently, you know that there was this wildfire um, incident somewhere around. I mean, there was even one in Canada more recently, let's say 2, 3 weeks ago, where there was a lot of smoke in the atmosphere that led to the air being polluted. And I mean, what they actually mentioned after that was that there was issues around, people having cough and cold. The clinics were reporting a lot of cough and cold incidents. And so what it means is that the quality of the air you breathe actually matters. And the intensity of pollution in the atmosphere could actually kill people, to be actually honest. So the definition of air pollution, let's quickly run through that and then get into the subject of, measuring the pollution that you have in the atmosphere. And then we'll then talk about correction of the measurements that you get from some of these low cost air quality centers. I mean, the whole idea of them being low cost is that you pay less money to get them, but then because you pay less money to get them, they are not as accurate as what you would have in the case of the reference grade monitors that give high quality measurements, which are super expensive to obtain. Okay, so air pollution is the contamination of the indoor and outdoor environment by chemical, physical, biological agent that modifies the natural characteristics of the atmosphere. And there are examples of pollutants in the atmosphere. There is particulate matter, there's carbon monoxide, there's ozone, there's nitrogen dioxide, and there is sulfur dioxide. So particulate matter is specifically known to be very, very a notorious pollutant in the atmosphere, and there are different types of particulate matter in the atmosphere. The sources of this particulate matter come from things like industrial power plants, smoke in the atmosphere. You could have smoke in the atmosphere from, cars. If you have a lot of traffic, think of a place like Lagos in Nigeria or, Delhi in India or some of these very high density, high volume traffic cities. Then you want to imagine that the air quality wouldn't be as good as what you would get in some remote village where maybe there are no cars or there's one or two. Right. So also you want to think about things like, wildfire smoke, volcanoes, cities generally have contributions to air pollution. Um, and like I already mentioned before, particulate matter is a very dangerous pollutant in the atmosphere because it's associated with, like I mentioned before, uh, cough and cold, asthma, and even heart diseases in many cases. Like for some of the work I'm doing right now is looking at how long-term exposure to particulate matter could actually increase one's chances of um, being infected with cardiovascular disease. and our results actually show that there is a significant effect of that. So particulate matter, I would call it PM in this case, and then we will call it 2.5 because we are specifically looking at PM 2.5, which is particulate matter with aerodynamic diameter of 2.5 microns. Right. So yeah, we have PM 2.5 in the atmosphere, and we want to measure because we know that people breathing in this PM 2.5 can cause disease, can kill them. So we want to be able to know how much of it is in the atmosphere per time. The Environmental Protection Agency in the US sets a threshold. Also, the World Health Organization has a threshold that is set at about 25 microgram per meter cube, or 35 microns, that you should have in terms of the volume that you should have in 1 coulomb of air in the atmosphere. And in the US, the Environmental Protection Agency sets it at about 12. And recently, in fact, one of the papers that we wrote this year, we were looking at recommending reducing that threshold from 12 to, because we find that even at 12, people still can get, can get affected and can still get killed. So we're looking at bringing it down to like probably 10 or 8, right? So you need to measure how much you have in the atmosphere so you can get an idea of this, what people are actually breathing in. And then, I mean, if you're going to reduce the pollutants in the atmosphere, you need to know how much is actually there in the first place, right? Right. So yeah, and the problem is in a place like Nigeria, for example, if you need to set up this kind of measurement systems in place, you are constrained by financial resources, which means that you need to go for low-cost sensors because you cannot go for the reference grade sensors. And if you go for low-cost sensors, you have to be able to correct them because the measurements you get are not as precise as they should be. So you need to correct whatever you get from them. And there are different ways to correct just sensors. You could correct them using nominal correction in laboratory. The problem with nominal correction is that it doesn't take into consideration the different effects you could have, using the sensors on different locations on the field, in the outdoor, in the real world. So it's not as effective as what we call model-based correction using, data from reference grid monitors. If you do not have reference grid monitors on the field that give precise measurements that you could then use for correction, then you can't go with nominal correction in the laboratory. Like for example, I know that there are projects in Africa right now where the locations do not have reference grid monitors, and what people do is they send the sensors, the local sensors, they send 1 or 2 of them to some laboratory somewhere in the world, and those ones will calibrate and send it back to them. You can see, right? But in most cases, you want to have a reference grid monitor on the ground, and then you want to use that reference grid monitor to calibrate the low-cost sensors that you're going to be having in the field. Let me give an example. In fact, right now we are working with a company in Uganda, Kampala. They make low-cost air quality sensors for African settings, and we are going to be installing those sensors. We are going to be installing about 50 of them in Madagascar and South Africa later in the year. And one of the things we did was to find out where they have reference grid monitors in these countries. For example, in the case of Madagascar, we found out that they have reference grid monitor at the US Embassy in Antananarivo, which is the capital of Madagascar. So we are going to be placing some of the sensors we are supposed to be deploying over the country. We're going to be placing some of them at that location so that we can be able to do this kind of correction that you're going to be learning today, right? And the idea is that you want to have a model that takes data from this reference grid sensor and takes data from this your own low-cost sensor, and then compares the data and then tells you how much your low-cost sensor deviates from a reference grid monitor, so that you can then be able to adjust for whatever that deviation is. And so that's essentially the maths that I've written on the screen there. Don't bother yourself about the maths too much. So for example, also very related to the Madagascar project I had spoken to you about, it's this Love My Hair program. It's in Denver, here in the US, where the government is trying to improve the hair quality of Denver. The local council is trying to improve the hair quality of Denver, but then they want to start from some of the places where you have the most vulnerable people, which are children, kids who go to school. So if you want to improve the quality of the air of the whole of just school environments in Denver, they, in order to be able to achieve that, they installed a couple of low-cost sensors. But then they co-located some of these sensors with reference grade monitors in in Denver. So we have the data on that. So that's the data you're going to be interacting with if you follow me as we go today. So let me just I don't know why my okay, yeah, let's go on. So right, so a colleague of mine at essentially manipulated this data, developed statistical correction methods for the local sensors that had been deployed in Denver. And her name is Ellen Considine. She's also here in the same group with me at Harvard. Um, and essentially, she compared a couple of methods, machine learning methods and statistical methods, for achieving this correction that I had spoken to you about. So as we go forward, you would see that some of the results that we get in terms of the correction that we achieved, and getting the best correction that is possible, requires that you also get some extra data sets or extra data from the locations where you're going to be deploying the sensors. And this data would include things like humidity and temperature. And the actual reality is that when you have good air quality sensors on the ground, they low-cost air quality sensors on the ground, they also measure temperature and humidity, and some of them even measure other kinds of pollutants like, NO2 or PM10. So that helps you also to be able to do a correction, right? So let's talk to you about the data. The data for this particular study that we're going to be, looking at. There is, of course, you need to have two data. If you remember very well, you're trying to correct readings from local sensors, and then you want to use reference grade monitors to correct them. So you need data from the reference grade monitor, you need data from the from the local sensor. So for our reference grid monitor, it's called canary sensor. You have PM 2.5 measured over time, and also the same thing for the low cost air quality sensor. For the low cost air quality sensor, we have data from 2018 to May 2019, August 2018 to May 2019 in 3 locations. And then we have from September 2019 to mid-December 2019 in 2 other locations. So we'll be doing this correction differently for these locations because they don't overlap, right? But then also, so let me just give a broad overview of how this could be done in practice. Because you have the data that is not overlapping in time, you could do correction for different times and then correct these sensors differently, or you could merge them and then include a time variable or multiple time variables in your model to account for those time differences, for example, right? And what are the ways you could include time variables in your model? If you're doing time series analysis or you're doing some causal inference analysis, you could include, for example, month of the year. You could include a dummy variable for month of the year, for example, and then you could include a dummy variable for the different years, and then you could include a dummy variable, in fact, for the different locations that you are installing the sensors in. So that would account for all of that, and in that way, you can even merge all of the data into a single modeling pipeline. So yeah, just to give you an overview, an idea of the data and what it looks like, and I've already explained before. The PM 2.5 is measured hourly from the sensors, both the reference grade monitors and the low cost sensor. In fact, the low cost sensor gives us every minute, so we average that to get to hourly. And then the other features that we want to include in our model, we have temperature, we have humidity. Temperature and humidity are also measured by the same low cost air quality sensors. And then you have distance to the highway. If you remember very well, roads are strong contributors to pollutants in an environment. So if you have major roads, like the interstate roads in the US, for example, which are like really large roads, in Nigeria, you could call them expressway. It's like looking at the Lagos-Ibadan Expressway, for example, which has a lot of traffic, for example, on a Saturday morning where people are coming into Lagos, or so those kinds of roads have strong contributions. Then so we are going to include that. We're going to include road lengths within a buffer radius, for example, because that gives you a sense of how much contribution can come into that space from cars and trucks. Then we will also include cyclical values of months and hour of the day to account for daily and seasonal variation. So yeah, that makes a lot of sense, because the idea is that the pollution during the night and during the day would not be the same, for example, in the sense that human activities, industrial components, and all this smoke contributions that do not come from natural hazards are come from human activities. There will be more of those during the day than during the night. So you want to account for the time of the day in terms of your correction, right? So also, because generally in machine learning or in statistical modeling, there is something we call, you have your training data and then you have your test sets. You want your test set to be independent of your training sets, because specifically you want to prove that your model is able to learn something and it can generalize into a new location. In our own case, new locations, right? So in this case, we select 3, right, for training, and then we select the 2 locations for tests. So yeah, taking into consideration all that we have said up to this point, we arrive at a set of questions, and we want to ask ourselves these questions before we get into the materials that I've shared with you from GitHub. And these questions are, first of all, if we get readings from low-cost air quality sensors in the field, and they are not as accurate as they should be, and we also get some readings from reference grid monitors that are very accurate, can we use those reference grid monitors to correct the readings from the low cost? The answer to that question is yes. How can we do it? We can do it using nominal correction in laboratory, or we could do it using models. So we have said that we want to go the model routes because it's more optimal. But then the question is, what kind of model can we use to do this? There are many kinds of models, and since you are data scientists, you probably know a bunch of models, right? And then the question is, what variables do we want to include in the model, and what's the contributions of each of these variables to the model performance? Things like that. These are the kinds of questions that data scientists would be interested in answering for this kind of problem. So yeah, in order to show that you've been listening, I'd ask 1 or 2 questions. If you're a data scientist and you want to do this kind of correction or this kind of modeling, what kind of model would you use? Or can you give me examples of models you've worked with in the past that you know about? Just type them in the chat very quickly. If you have worked with any model for statistical modeling, machine learning, whatever, just drop it in the chats, what the kinds of models that you are familiar with or that you have used. Okay, someone said ARIMA. Okay. Someone said random forest. ARIMA is autoregressive integrated moving average. That's a very interesting one, actually. So ARIMA was not applied to this because ARIMA is for time series modeling. Someone said ResNet. Okay. ResNet would go for image processing because that's convolutional neural network, which right. So yeah, with skip connections. Decision tree, okay, that's good. And then random forest is just an ensemble of decision trees. Do we have any other ones? Anybody else? Anybody else? Autoencoders are not autoencoders are not specifically models. An autoencoder is an architecture of neural networks, specifically. So you could say neural network has the model, but an autoencoder is a specific architecture of neural network. Someone said he has a question. Oladimeji Williams, can you please drop your question? Drop your question, please, before we proceed. Okay.
Okay, can I just talk?
Yeah, please go on.
Okay, so I saw that from the training set, it was collected from a particular location, and that the test set is from a particular location.
Yeah.
Well, coming from a theoretical background, will it not affect the generalization of the model since they are from different locations?
Right. That's a very good question. Thank you very much. Thank you for that question. Right. Fair enough. Let's think about it in this way. When you want to do modeling, you want to think about what your goal is eventually. What is the goal of the statistical correction model? The goal of the statistical correction model is you want to use low-cost sensors that have been co-located with reference grid sensors. You want to calibrate those ones, and then you want to now take that model into the real world. So calibrate a bunch of other sensors in that same city, for example, in Denver, that you have not been able to co-locate with any reference grid sensors, right? What does that mean? It means that your eventual goal is to ensure that your model can generalize into locations that the model had not been trained in before. So that essentially makes it, in a sense, mandatory for you to actually ensure that when you're doing your testing, you're testing in a new location that had not been seen by the model before, because that's exactly your goal. Because eventually, when you're going to be deploying this model, it's going to be deployed over sensors and locations that you have not trained your data on, actually. So what actually changes is not time, because you will cover the whole time, right? For all of the sensors, you have all the time covered, but then new locations. For example, think about it. We are only looking at 5 sensors here because we only have 5 sensors that are co-located with reference grid monitors. But how about you think about the fact that the actual sensors that have been deployed in the field are, running to 50, for example, right? So that's the point. Does it make any sense? Have I communicated anything, Olajimeji? Are you there?
Yes, it does. Thanks.
Okay, yeah, cool. So that's the idea. So yeah, a bunch of you have worked with ARIMA, a bunch of you have worked with random forest. So has anybody worked with linear regression before? Just put a yes in the chats if you have done that, if you worked with linear regression in the past. Just put a yes in the chats. Yeah, you've worked with it. Awesome. Awesome. Okay. So yeah, so you could think about this as a linear regression where so if you want to do it as a linear regression, for example, I'd like somebody to come on and talk, actually. If you want to do this as a linear regression, for example, you know that a simple linear model is y is equal to mx plus c, where, okay, yeah, multivariate linear regression, simple and multivariate. So let's look at a simple linear regression where y is equal to mx plus c, where m or beta x plus c, where c is just an intercept, and then beta is the coefficient of x, which in this case, so what should be your y, what should be your x in that model that I just described right now? Let me write it in the chat. Y is equal to beta x plus c. So if you have this kind of model where y is your outcome, x is your x is your input variable to the model, y is your outcome. If you want to do a statistical correction using this kind of model, and you have data from low-cost sensor, you want to correct it to the one from reference grid sensor, what should be your y, what should be your x in this model that is written in the chat? Anybody? Anybody? Are we there? So Oladimeji, do you know this one? So because we don't want to waste our time, right? So okay, x, okay, cool. Nathan said, I suppose x is from the local sensor. And then what is y? What should be y then? That's correct. Thank you, Nathan. That's very correct. So you guys are very, very solid data scientists. right? So that's a good one. So X, of course, is from the local census, and then what would Y be then? Y would be from the reference grade. So I mean, someone is probably typing that already, but I just wanted us to move on very quickly. So Y would be, yes, is the reference grade. Grade is not rate, so reference grade monitor. So that would be the case. Yeah, exactly. But in our own case, right? Because you're going to be doing a multivariate linear regression in this case, because in our inputs we are not just going to be having the low cost PM 2.5. We also want to remember we're going to be adding a bunch of things, including temperature, including what else are we in? If you remember very well, if you're going to be putting PM 2.5 from the local sensor, we're going to be putting temperature. What else are we going to be putting again? Can someone just type something in the chat that tells that the multivariate linear regression we're going to be fitting, because that's what we're going to be doing. Humidity, yeah, thank you. What else again? After humidity, Olamide Williams is doing a very good job today. There's also Nikita who has said humidity, and then we want to look at length of road within specific radius to the point where you have the sensor. And then what else again do we want to add? Do we want to add to the model? Time, exactly, time of the day. Why? Because you want to be able to account for the time when that reading was actually recorded and registered, and then to do the correction. For example, if you get a very high value of PM 2.5 in the middle of the night, that's very unlikely, right? I mean, you could have that in the case where there is fire burning, right? But that's very unlikely on a normal day, right? And so you want to account for time. Okay, so let me unshare this screen and then let's go to the code and then quickly just run through them. I will not bore you when we're doing that. I'll just quickly, it will be a very fast, a very quick process, but then we will be interacting the way we are interacting in the chats. So let me stop sharing my screen now and then share a different screen where we'll be talking about the code together. Awesome. Okay, so if you have seen what Messi had sent to you or whoever had sent it to you, you probably had gone through, and if you've not, we can do it right now together. If you come into the repository, you find that there is a bunch of lessons. There's lesson 1, data preparation. There is lesson 2, exploratory data analysis. Lesson 3, modeling, and there is lesson 4, which is leave one. Okay, there's leave one location out, cross validation. It's called LOV, right? Leave one location out, cross validation. We're gonna get in cross validation is a different. Have you has anybody on this call ever heard of cross validation before? Cross validation. Put a yes if you have. If you have you ever heard of cross validation before? And why do you do cross validation? For example, can someone just tell me why you do cross validation? Because I think you're already going towards that. Somebody asked a question earlier about why are we testing in a different location? So yeah, so why do you do cross validation, for example? So why you do cross validation is because, so for example, look at the way we did it. We have 3 locations for training, 2 locations for testing. Okay, cool. Yeah. So someone said yes, right? Okay, yes. All right. So we have 3 locations for training, 2 locations for testing. So then what do you want to do? You want to ensure that your model is not specifically built for the case where those 2 locations are you used to train, your model overfits over those 2 locations, and then also in testing overfits over those 2 locations. You want to be able to be sure that if you change the test and you switch, for example, some of the, yeah, exactly, to prevent overfitting. Thank you very much, Zed, you're correct. So you just want to be able to be sure that if you change the test to training and you switch some of the training to test, your performance is still very, very, comparable in that way. So then so when you do cross validation, you iterate, you change, remove one location, and then you rerun the model, and then you see what you get. You understand? Okay, yeah. Oladimeji Williams said it's used to solve overfitting. So yeah, the first notebook you have here is data preparation. Most of the time when you get data in the real world, if you're working in a company or you're working somewhere, they told you to calibrate some sensors or do some, what happens is that the data is not the way you have it, you want to have it. So you do some cleaning of the data, and then you format the data to get to a particular structure and standard that you want to have it. Ideally, you want to have a data frame where one of the columns of your data frame is your so every row of your data frame is a time point, right? Specifically, and then time points for a specific sensor or a specific location rather. Then every column is now, the reference grid measurement, the low cost measurement, and then temperature, humidity, length of road, time of the day, month, that kind of thing. You understand? So you want to be able to create that kind of data, right? So that's what we do in this particular notebook. I don't want to bore you with that, but the eventual outcome is that you have something that, that in that sense is regular and well behaved. So now let's go to the second notebook, which in this case, has any one of you run all of these notebooks here? Did any one of you run them? Say yes in the chat if you did. So right. So Arundarasi, you ran the notebook. Did you have any problems? Did you find out anything interesting? Were you able to run everything successfully? Okay, someone is saying we should send a link to the notebooks. All right. I'll drop it in the chat now, just a moment. All right, so just give me a second. Let me drop it in the chat. Just for those who don't have them yet, these are them. It's just that if you're just getting the link to the notebooks now, it might be too dense for you. So I'd advise that after the session, you go over them in your personal time and try to figure them out. But then I want to condense the whole thing into stuff that you can quickly understand, right? So data preparation is just getting the data and then cleaning it, removing missing values, all those other things. I mean, has any one of you dealt with missing values before? If you have missing value in your data, have you had to handle things like that before? Just say yes in the chat if you've had to. So yeah, so what are the ways you could handle missing data? What are possible approaches to handling missing data? Can you just drop you can drop one, just drop one that you feel a value, fill with a value, drop. Yeah, okay. Interpolate, median, mode, mean. Okay, that makes sense. Wonderful. I mean, I see that you guys are very conversant with handling missing data. What are other ways you could handle? Yeah, careful observation of other columns. Yeah, exactly. So you could at times just observe other columns, and for example, at times, let's say you observe other columns and you realize that within the particular time frame where this data was missing, the value is constant. In fact, so you just fill that same value in, and that would especially even be automatically handled by interpolation specifically. All right. For this kind of data that we have, this multi-site data that we have, prediction, yes, you can predict missing data. Yeah. Oh, wonderful. Tobiolowo, ask from someone with domain expertise. That's a very, very important one. And people ignore this. A lot of times people just take data and say, hey, I have this data. Boom, I want to work with it. They don't interact with domain experts who can help them interpret the data and then undo problems like missing data, for example. So that's wonderful. Thank you very much, Toby. In our own case, and we will be dropping observations with missing data because you could also drop them. That's another one. Nobody mentioned. You could actually also drop. So when you're doing interpolation or adding missing data in many ways, you have to be careful. And some of the things you have to be careful of is specifically Right. So it's specifically the fact that you have this data coming from different sites, so different locations. You have 5 different locations. For example, in your training, you have 3 different locations, right? So if you are doing interpolation, for example, you want to interpolate for every location so that you are interpolating for that location with data that come from only that location. You're not just interpolating the whole data. You understand specifically. So that's very, very important if you're using interpolation, for example. All right. So then you don't do exploratory data analysis. So let's say given the kind of data that we have already, which is, you have the reference grade, the low cost, and then temperature, humidity, and the likes. If you're going to do exploratory data analysis on that kind of data, what are the kinds of things you imagine you need to check? What are the kinds of what are the things you need to look at, for example, in the data, just to explore and check if you're going to be doing that? Someone is saying, I'm not seeing your screen. Oh, really? Are you all seeing my screen? Is everybody seeing my screen?
Yeah, we can see your screen.
Awesome. Okay. So Oladimeji Williams said seasonality of the highest temperature. Okay, so let's not focus on temperature right now, because temperature, in fact, is one of our covariates. It's not a main variable that we are going to be putting that we are considering, because the main variables we are considering, think about them, there are 2. There is a reference grade measurement and there's the low cost measurement. You get, yeah. So those 2 themselves, if you want to statistically correct the low cost measurement, you're assuming that they are different from the reference grade measurement, and they are different significantly enough to require you to do a correction. Right? Does that make sense? So based on what I just told you right now, what do you think you need to check? So what do you need to check? You need to check a couple of things. Correlation between, oh my, that's wonderful, actually. Right. So you want to check the correlation between the reference and the low cost. Someone said you want to check wind speeds. Well, we're not measuring wind speeds in this case. We don't have data on that. But if you do have, that would be useful to check. Right. Right. So some of the questions we're going to be you could explore when you're doing this kind of outliers, for example. Yes. So you want to check for outliers in your reference measurements and your low cost sensor measurement. So, but there are a couple of there are many things you want to check. So then I have written out a list of questions here. These are just some questions. Imbalance in the data, exactly. And how do you check for imbalance in the data? How do you do that? Someone said imbalance in data. How do you check for imbalance in your data? Yeah, you can check bar plots and it's yeah. You could use modes. All right, interestingly, right. Yeah, you could use modes. Modes is specifically for if you have imbalanced samples, right? So modes is specifically for balancing. So when you have imbalanced samples, you could do balancing by, for example, subsamplings some of the cases where you have a lot of measurement. But the reason why you don't have imbalance in this kind of data that we're talking about is that you could have imbalance after you drop missing values. Eventually, what happens is that for every single location, you have sensing for every hour of the day across the same amount of time. So essentially, you're not going to be having the balance problem. For this problem that we are addressing. You get, so balance is not going to be a problem in this case. So then let's go on. So first of all, you want to ask yourself, so what is the geospatial context of the locations of this sensor? That's one question you want to ask yourself first. So you say, oh, there are 5 sites that are being considered, 2 for training, 3 for training, 2 for test. You want to even know what does those locations look like. So you get the longitude and the latitude, of those locations, and then you plot them, and then you look at it and say, hey, so I am choosing this one as test and this one as training. I mean, am I sampling, is my sampling random enough? Am I using 2 locations that are just beside themselves for test, and then 3 other locations that are just right beside themselves for training? And then I'm telling myself I'm building a training and a test set, which in reality might not be the case, because you want to randomly sample your data, in the sense that, you know, you're not just choosing clusters of locations in training and in tests. So you want to check what is the geospatial context, right, of these locations, right? So if I were you, I would, after the session, go to those notebooks and then try to look at how all of these things that I'm talking about have been specifically done, and then, run them, check the outcome and all that. And then if possible, even write a blog post, do a blog post for yourself that you share with your community, with your friends, that you can put your resume, you understand, some of the stuff you worked on. Anyway, so, and then you want to check, for example, the summary statistics of the reference grade and the local sensor. So some of the things you could check, for example, just check the average for each of the locations. Check the average for the reference grade and the average for the low cost. What you might find is that maybe one is lower than the other one. That is already even a statistical correction. If you, for example, it's a very naive one. It's naive because it doesn't take into consideration things like time of the day and all that other things, right? But then a very naive correction here is just your average for each of the locations across the 2 sensor category, and then you just do a bar plot of these averages, and then you look at the difference between those averages. If, let's say, the low cost sensor has a lower average than the reference grade, you look at what is the differential between those 2, and then you apply that differential to each data that you collect from the local sensor. You just mark up whatever value you have from local sensor by that value, and you have done a correction. In fact, you have not done no linear regression or nothing, just looking at averages. Somebody talked about correlation. Yeah. One of the ways to look at correlation is scatter plots. So if you do a scatter plot and the correlation is, you would see the direction of, ideally what you want to have is a perfect correlation, right? But what you would get is that you will see the scatter plot, you will see that the correlation is shifted a little bit, either, up or below. And what's your correction is supposed to do is to do like this rotation, so that you can get a perfect correlation, right? So you could do scatter plots, histograms, right? So an histogram just gives you the distribution. So what you want to get in that sense is you want to have distributions overlapping perfectly, right? But they would not overlap because, that's why you're doing correction. And then also we want to ask the question of, so time, because we're including time in our model. So do we have differences in time? So for example, for every location, if you average your readings for across all the days that you have readings for every time of the day, for example, what is the average reading you have at 1 o'clock, at 2 o'clock, at 3 o'clock, at 4 o'clock, 5 o'clock? And then you look at it across the whole time, and then you see, do we have variation in time? Does time affect what we are measuring in any way? If everything is more or less the same, you could just drop the time variable, because then it's not useful, because you don't have variation in time. It's not changing specifically in time. So these are the ways to, it's more important to understand why and think about the problem in this way than just having code and then running the code. Blah, blah, blah. No, that doesn't help you at all. You want to frame questions in your mind and say, okay, you know what, and then check them out in the data. So in addition to all of those things that I have mentioned, what else do you think? What are other things now? Since I have said a few things now, what are other things that come to mind that you think it might be useful to check in this data? You understand? Can anybody tell me something? Because we have like 10 minutes to go. So I'll just quickly run through the modeling notebook, and then immediately after that we'll take questions. Yeah. So yeah, like you mentioned, someone said random forest for modeling, someone said linear model. In this notebook that I'm showing you, we focused on linear model and random forest for correcting the sensor readings specifically. So I'll take you to where that has been done. If you load your data and then you do a modeling, boom. For this particular model, in this case, you're not you're not doing multivariates. In fact, so when you want to do modeling for this kind of work, you don't just jump in and start doing the multivariate modeling. You always start from the simplest one, and then you want to have y is equal to mx plus c, low cost reading, reference grid monitor reading. That's all you have in your model. So low cost reading goes in, reference grid monitor reading comes out on the other side, and then you want to check that. And if can we have the notebooks? I remember I dropped them in chats earlier today. Let me just redrop it again now. So when you're doing modeling, for example, you can start from just one variable, not a multivariate one. So then you can then begin to scale. What is important for you to check when you're doing this kind of thing is what you want to check is you want to check that you're not just you don't add complexity for no reason. So for example, if you had extra variables, let's say you had temperature, you had humidity, you had load, all this fancy stuff that we spoke about. If the correction performance does not improve, then you realize that there's no point. Let me just do my simple model. Input one variable, output one variable. But then there's a very important component of modeling, which is where I'm going. That's the last set of questions I'll be asking you. So how do you know that your model is good, or how do you have a measure of the performance of your model? For this particular case, it's a regression. You have continuous values in the in input, continuous values in output, or in outcome. What is a metric, for example? Can you give me an example of a metric you could use to measure the performance of a kind of model? There's the R squared. Someone said R squared. Yeah, that's correct. That's correct. Yeah, R squared is 1. Accuracy, no, you can't use accuracy. So yeah, the mean absolute error, MAE, the root mean squared error, Abdul Salam, Ibrahim, thank you. There's Gideon Moazu, he said mean absolute error. That's correct. You can't use accuracy for this. Accuracy specifically means that you are categorizing stuff. Yes, the RSS, yes, yeah. Okay, then that's the residuals. And then you have the R squared. Exactly. And what do you want to have? What do you want to do most of the time? You want to have multiple measurements. Or most, no. The F1 score is not Absalam Ibrahim. The F1 score is specifically for classification problems, right? Where you are grouping stuff. In this case, you are doing a regression, so you're not using F1 score. All right. So let me see another question that is useful to ask. Okay. So yeah, what can you also, if you have your linear regression model and you pass this different covariates into the model. Let's say you eventually use temperature, humidity, roads, blah blah blah. What else can, beyond the model performance, what else can you see from the model? Especially, for example, looking at the coefficients of the model, for example, what can you do with those coefficients? You see, let's say there are coefficients for, the low cost reading, there are coefficients for, you have coefficient for temperature, coefficient for humidity, and then you see all these coefficients across the different variables. What can you use that coefficient to do? Anybody?
I think it can help you to know which of the columns to drop if they are not contributing well to the model, to the visualization.
Fantastic. That's a wonderful answer, right? So you want to explain your model, you can drop, right, and say, okay, you know what, this guy here is not, it's not contributing anything and stuff like that. Yeah, that's a very good one. So yeah, so mostly when you have those kind of models, you want to look through them and then check through the coefficients of your model. And this is the advantage of working with linear models. And then you can check. And then random forest also has this feature importance that you can use to do something similar, right? The variance inflation factor. Well, those are interesting stuff you could also do. Someone's talking about using the VIFs, Oladimeji William. Yeah, I mean, there's a lot of fancy stuff, but you don't want to go that complicated routes. It's just, this is a very simple R squared, RMSE, performance evaluation, because essentially your goal is just to calibrate, right? In fact, if your RMSE is 0, you're fine and you move on, right? So you want it to be as close to 0 as possible. The problem with RMSE, however, is that, so how do you know what is a good RMSE, right? Because it's any number can be an RMSE. It's like from minus infinity to infinity, rather, well, no, from infinity to infinity, right? From 0 to infinity, essentially. Sorry, it's not minus infinity. So from 0 to infinity. So how do you know? So that's the problem with RMSE. That's why at times I advise people to use things like the mean absolute percentage error, the R square. Things that actually are bounds, that are bounded. The R square, for example, that if it is 1, then you have a good result, right? So as close to 1 as possible. The mean absolute percentage error tells you the percentage of error that you're committing in terms of, with respect to the baseline. So those are all the measures you could use. Mapping. That was not used in this notebook, for example, but I would use that. So in this case, for example, we had multiple models. We had just PM 2.5, just the low cost reading, and then we had low cost reading plus temperature, and then we added road length, and then we added hour and month. And then, just checking if all those variables actually improve the model in any way. And those are the results essentially for the different location. If you train, and for different location, this is what you get. And then you see that if you have a baseline, this is the baseline error, and then this is the error after your modeling. And how do you get the baseline error actually? How do you know that your model has improved, has calibrated your sensor? Can you think about that for a moment? Someone is asking a question. Please, is correlation what we used to know what relates to what variable to plot against another? Well, correlation is simply looking at the relationship between two variables and how well they go together, right? How well they actually, go together. So if one of them is increasing at the same time as the other increases, and then when this one is decreasing, that other one is also decreasing, then you say they are highly correlated. You get. So correlation is that. All right. So I wanted us to think very quickly about something before we go into questions. How do you know that your model has actually improved something or is useful in any way? How you know that is very simple. You take your data without the model, so your reference grade monitor and then the low cost sensor monitor, and then you just do an RMSE of that, right? You understand? You do an RMSE of that, and then the outcome of your model, you now do an RMSE of that with your reference rate. And what that helps you to do then is to see that if your model actually improved anything at all. And that's what has been done here. And you see that in this case, the model actually improves things it reduces about 50% of the error you get. In many of the cases, if you check from top to bottom, you find out that in many of the cases, it's like 50% reduction of the error, which is significant. That's a lot, So we have a good model, boom. We are, we have done a good job. So yeah, thank you very much for listening to me thus far. Please take the time to get through the notebooks, and then if you have any questions, you can, forward them to your tutor or your to your tutors, and then they can send them to me. They know where to reach me. Thank you very much. So if you have any questions at this point, you can drop them very quickly, and then I'll be reading through the chats to just answer any questions. How do you know how much a feature is contributing to a model? Yeah, for a linear regression, for example, the features that are making the highest contributions have the highest coefficients, right? So y is equal to beta x plus c. You remember very well, right? But in this case, y is equal to beta 1x1 plus beta 2x2 plus beta 3x3 plus an error term, right? So you can then compare beta 1, beta 2, beta 3, right? Which one is the highest? If beta 1 is the highest, then x1 is giving the highest contribution. If beta 2 is the highest, then x2 is giving the highest contribution, and and things like that. So these are very interesting. That's a very interesting question, right? Yeah. So you just look at the coefficients in your model, and then you rank the features by their coefficients to know the ones that are contributing well to the model, right? That's for linear regression model. For other kinds of model, there are different ways to do that. Okay. Do we have any other questions?
I don't think there are any other questions for now, but we'll be on the lookout.
Okay, cool. Thank you very much. I really appreciate it.
Thank you very much, Mr. Ladimeji, for that session. I'm sure that everyone in attendance has learned quite a lot. Just before our speaker takes more of your questions, we would like to tell you there's a second attendance form that will be dropping now. And please, the secret code is pandas, all lowercase. So the secret code is pandas, all lowercase. So the form will be dropping now in the comment section of YouTube as well as Zoom here. So please be on the lookout and fill the form. You know, it lasts for only 10 minutes. Okay, so we have another question in the chat here.
Where is it?
Okay, I mean, I think
we already answered the question that is in the chat. So yeah, that's
Okay, I thought I saw another question. Looks like we've answered all.
Are you checking the comments on YouTube? Do you have questions there?
Yeah, we're monitoring that too. There are no questions from there for now.
Cool, thank you. All right then.
Okay. I mean, we could give out a couple of, I don't know if you have any other questions for the interns while we wait to see if they have any other questions, or we could just have them refer to you later if they have questions.
Yeah. They can reach out to me later, anytime, if they have any questions. I would advise that maybe they'll batch their questions and send them to you, and then and then they can then forward it to me, and then yeah, for sure, why not? Yeah,
Okay.
but they've been very, very responsive, and yeah, great job.
All right. Okay, so someone is asking, how do we reach out to you?
Well, I mean, LinkedIn is one of the is somewhere I reply LinkedIn messages very I check LinkedIn. I mean, at least once every week I do check LinkedIn. So email is tricky because then there's too many emails coming in these days. So you can, well, LinkedIn is like the most effective right now. So I want to drop in the chats.
Okay.
So yeah, I dropped my LinkedIn in the chats. Awesome.
Okay, thank you very much. So with that, we've officially come to the end of today's webinar. A big thank you to Mr. Ladimeji for taking the time to educate us today. Okay, so Adeni, he has dropped his LinkedIn, and of course we'll be sharing the notebook as well as other resources with you.
All right, I appreciate it. Thank you very much.
Okay, so thank you. Every second has been totally worth it. So I want to thank our dear interns and visitors for joining us today. I'm sure that you've gained valuable insights and knowledge. And so a big thank you as well to the Hamoye team and everyone who saw to the success of this webinar. Until next time, we hope that you do have a lovely weekend. Bye, everyone.